Hello and welcome to this next session on the use of an infrared spectrometer. Here we'll be talking about infrared spectroscopy, especially as it pertains to the spectrometer components within an infrared spectrometer. So FTIR spectrometers typically look like something that we have here, this JASCO FTIR, where you can place the sample somewhere within this chamber part here, and the rest of the components are within here. There is going to be a light beam which will pass through this chamber, which will be used to measure our sample. So in an FTIR spectrometer, we have, of course, lamp sources because we are dealing with molecular absorption spectroscopy of a particular form, i.e. it is inside of the infrared region, whether that be the near IR, mid IR, or far IR. So typically, whenever we're doing this, we're going to be using mid IR. So we'll want to choose a lamp source which is going to produce light in that region. And typically that will be the tungsten filament lamp. There are others available, such as this Nernst glower, which is a heated rare earth oxide rod, which can reach temperatures of about 1500 degrees Kelvin. But since that is contained within the spectrometer, we don't need to worry too much about that, so long as we handle the spectrometer correctly. We can see that it produces a broad range of wavelengths, going all the way through from the mid to the far IR. We have glow bars as well. That's heated silicon carbide rods. Those are kind of a black body radiation source. They produce a broad infrared source. Tungsten filament lamps, temperatures around about 1100 Kelvin. This is the one probably most common because of its relatively low cost, and also the fact that it covers the majority of the mid IR region, which is generally what we're measuring. It's usually the most meaningful for our measurements. And we also have things like mercury arc lamps, carbon dioxide lasers, which are useful in different regions. So after we have produced our light and it has been absorbed by our sample at particular wavelengths, we'll want to know which wavelengths have actually been absorbed. And to do that, we'll need to use a transducer, which will produce the electrical signal, which will be what we are actually measuring. As much as we may want to measure the absorbance directly, it's not really possible. And so what we must do is we must measure the difference in the absorption versus the incident beam versus the exiting beam after it has passed through the sample. And so there are a number of different transducers that we can do. These will convert some sort of photoelectric effect to electricity. So a thermocouple, for example, uses the thermoelectric effect it's composed of a dissimilar metal junction, and it's very cheap. So most low-cost instruments will use this, but its low cost does come with some problems in that it is slow and insensitive. Ballometers, then, those are a different kind of thermistor. These are resistance thermometers. They need to be cooled to low temperatures, but they're highly sensitive, especially below 400 wave numbers. Pyroelectric transducers, then, these are usually piezoelectric materials. They're fast and sensitive and very good in sort of the mid IR. So we have here a piezoelectric, piezoelectric material here, transducer, and then we have a photoconductor. These are kind of like the CID arrays that we have. Usually this is in most modern high throughput FTIR instruments. We have these CIDs, these arrays of photoconductors. The reason why we do this is so that we can take the whole spectrum in one go. And so we're not just limited to the same as our UV vis, where we measure wavelength by wavelength. So the experimental methods then, so we have two different types of spectrometers. We have dispersive, which is the more traditional kind, and we have Fourier transform spectrometers, which is the general FTIR instrument that we have now. So dispersive spectrometers would not be called FTIR because FTIR stands for Fourier transform infrared. And those spectrometers make use of a different technique, which we will be looking at shortly. So dispersive spectrometers, as opposed to the capturing the whole spectrum in one go, they are scanning instruments, much like the workings of our UV-Vis spectrometer. So we have two types. We have a scanning type here, which is shown here. So this scans the different wavelengths which are absorbed by the sample. So the sample is somewhere outside of this setup here. The light that has passed through the sample is passed into this, where it is dispersed on a grating, and the spectrograph grating disperses the light, which is then further manipulated by the mirror, and then it's projected, the image is projected onto the slit, and by twisting and turning the different components, the mirrors and the gratings inside of this spectrometer, we can get the reading of the absorbance at different wavelengths. So the grating rotates, and signal at each wavelength is measured in turn, so each lambda, each wavelength. And this is similar to UV-Vis, but the sample is instead placed before the monochromator. So in UV-Vis, because of the way that the absorption was high energy there, and we wanted to make sure that we were only getting excitation events from one wavelength, we set up the monochromator before the sample so that we could isolate a single wavelength with which to excite the sample. Here, we're not doing that. We're exciting with polychromatic light of all the wavelengths that are available. We won't see any electronic transitions because remember that the vibrational and rotational energy levels are much, much lower in energy than the electronic energy levels that we are measuring in the UV-Vis. And because of that, we're able to just use the broad spectrum polychromatic light. And so it goes to the detector. The detector creates the electronic signal, which is what we're actually measuring, which is then passed to our computer for a readout. So here is the polychromatic white light source. It sort of like is a bulb, so light goes in every direction. It is then focused onto the sample through a collimating lens, which creates parallel beams of light, which pass through the sample, and then those are focused into the spectrometer, where the monochromator will separate the wavelengths of light, so then we can measure them using the photodetector. We have multi-channel dispersive spectrometers. So these are making use of CCD detectors, which are sort of arrays of photodetectors. So the grating here is set at a fixed angle, and signal at 1,000 wavelengths are measured simultaneously. So what we're doing is this CCD detector is set up so that each pixel will absorb will absorb a single wavelength, and that wavelength will be determined based on the position of the grating and the mirrors. So the grating, before the grating could move in the dispersive, but in this multi-channel instrument, it is fixed. And so it is incident on the CCD detector, all of these different wavelengths, and we see that we have the ability to measure more than one wavelength at a time. This creates a multiplex advantage in that we are able to have a higher throughput, and we are able to measure all the wavelengths at once. And so we're able to do more complex studies than would be possible with the scanning dispersive instrument that we saw on the previous slide. Then Fourier transform spectroscopy. So the underlying principle here is that the measuring a fluctuation against time is equivalent to measuring a frequency. So this is a mathematical operation. So we have a few things where we have a time domain spectrum and the corresponding frequency domain spectrum for what is assumed here is that this frequency domain, or sorry, this time domain spectrum can be converted into a frequency domain spectrum, because this is a series of waves which are characteristic of our molecules' absorbances of the infrared wavelengths. So whenever we decompose this using a Fourier transform, we will obtain a frequency domain spectrum, which will tell us the frequencies which are being absorbed. So you can see that some of these are very complex. And so once this is deconvoluted into its individual components, we can obtain different frequency spectra. So the underlying principle here is that we're measuring a fluctuation against time, and that this is equivalent to measuring a frequency. And this mathematical method carrying out the conversion between the frequency and time domains is the Fourier transform, which allows us to go from this, a series of time domain frequencies, to this, which is the frequency domain, which gives us the absorbance at a particular wavelength. So from that Fourier transform, we can see two different frequencies overlapping. So if we have a frequency A and a B, we can see their individual forms here. But whenever they are combined, they obviously go through constructive and destructive interference, which creates a resultant waveform of this type here, which can be deconvoluted into this frequency here. Now, if we have one which has a smaller difference, we can see this beat formation here. Like we can see there's a smaller amplitude and larger amplitudes here. So this is the resultant waveform from two frequencies which have a smaller difference than here. So we can combine multiple different waveforms to create a resultant waveform, for example, here where we have 6 different frequencies all shown at once. And so what we're really seeing here is a very complex beat formation or a frequency formation for a waveform which contains 6 different frequencies. Those can be deconvoluted via a Fourier transform, which is not something that we'll cover in this course, but the Fourier transform allows us to take this resultant waveform and deconvolute it into 6 different frequencies, which can be displayed on a spectrum. And so that's really what's happening, underlying principle of our infrared spectrometer. So here we have an example of the frequency distribution of a broad spectral line. Here you can see the broad spectral line, and then the different frequencies that make up this line. So like there are various different frequencies around about this broad line, which is the resultant form. Now we can see here, if the line is not infinitely narrow, then the interference between different components of the overall envelope distorts the frequency domain signal, which is this one. So that's the broadening here is caused by the overlap of the different frequencies inside of the waveform. And then here we can still see that there is a beat structure present whenever we have the 2 separate frequencies in the frequency domain. So we can have what seems to be very well resolved peaks, but actually the waveform is still pretty complex. So the general principle here is that we are recording the oscillating signal that is emitted or transmitted by a sample, and we are transforming it into the individual frequency components, i.e. the spectrum. So this is the Fourier transform equation, which again, as I said, is not something we necessarily need to concern ourselves with too much, albeit this is something to be aware of, that what we are actually measuring is the oscillating signal. And then through some mathematical operations, we can convert that into the absorption spectrum that we see. And so the power of this is that it's much easier to measure the whole spectrum at one time rather than having to measure it individually. So we record the waveform as a function of time, and then we can transform it into the frequency domain using our Fourier transform. And so the advantage of this is that all the frequency components are measured simultaneously. So because we're measuring the waveform, there's no need to measure individual wavelengths, because we can just measure everything in the waveform at one time and then convert that directly into our frequency spectrum, which gives us a great deal of power in our ability to measure things quickly and do things like kinetic studies. So the approach is easiest to visualize as interference between and detection of a series of oscillating emissions, but also works for absorption of lines from a continuous background. So here we have the display of 2 frequencies here and here. So we have number domain spectrum of a broadband source with a narrow absorption. So the absorption is here. And this is a wave number domain of a broadband source and the corresponding interferogram. So this interferogram is what is actually measured by our FTIR spectrometer. Actually, you can view this in the software usually for the spectrometer. You can see this, and this is one of the ways in which you can tune your infrared spectrometer to make sure that everything is working as it is supposed to. So some of this is just the information from the light source. So you can see here, there's no absorption. So this is the start of our light sources and frequencies, and this is the end of our light sources frequencies. So you can see here that there's no absorption. And so what we have here is just simply the detector signal as a function of what is emitted by the light source. But if in this case we put something there which can absorb, we see that there is a depression in the intensity. So you have an absorption peak. So this would be our kind of frequency domain spectrum. But this is then based on the interferogram, which is here. You can see that there's a difference between this one and this one, in that there's a lot more noise, or what appears to be noise, either side of the central point. So the central point here, once we go beyond that, it's kind of flat, right? Here you can see there's a lot of noise. This is actually where our spectral information is, here and here. So this is kind of the characteristic of the lamp in the middle, and then this is the spectral information. So finally, in IR, we can't measure the waveform directly because the frequency is too high to follow up and down. So instead, we modulate the broadband emission from source by sending it through an interferometer, which is the thing that we're measuring and we saw on the previous page. If the drive motor along obtains a periodic rises and falls in intensity at any given frequency, we can monitor this instead of the electric field intensity in the radiation directly. So this is what's called a Michaels interferometer, and this is going to kind of revolutionize the collection of infrared spectra. So the mirror moves with high precision over the total length of about 1 centimeter. So we have here a moving mirror. We have a stationary mirror. We have our light source, which is coherent. And then here we have our sample and our detector. So what we're doing is we're creating two beams. So whenever it goes through the beam, part of the beam is reflected onto the stationary mirror, and part of it passes through to this moving mirror. So we can move this mirror back and forward to create different waveforms with different path lengths. So these path length changes give us the ability to sample thousands of points at different times in the scan, and therefore we can get different path length differences, which give us different frequencies at the source light impinging on the sample. So here what we have is the coherent light source from our light source, such as maybe a tungsten lamp. Then it passes through, well, some of it passes through to the moving mirror, and some of it is reflected to the stationary mirror. And then this creates differences in path lengths, which allows us to measure the frequencies of light that are going to be absorbed by the sample. So the split beam is half passed through the moving mirror and half passed to the stationary mirror. The movement of the mirror enables us to delay the split beam by some fraction of a second. And then they're both recombined here at the mirror again. And then the sample will kind of be subjected to this different way, or like the different combinations of the waveform, which will give us the ability to look at periodic rises and falls in intensity at any given frequency. And this can be monitored instead of the electric field intensity, and thus we can get our spectrum much easier by measuring it at the detector. So by measuring the sort of differences between these two waves, the one that's delayed and the one that's stationary, we're able to sort of pick up on any differences between them. And these differences between the the standard beam, I guess, the one that is coming from the stationary mirror, and the delayed beam, the one that comes from the moving mirror, is what we're going to detect, and allows us to sort of look at the difference between those two. And by looking at the difference between those two, we're able to just sample a lot of wavelengths very quickly. So the advantages of FTIR instruments. So we have a throughput advantage. So we don't have a lot of optical components, just two mirrors, one of which moves. If there are no slits to attenuate, which means that we have high radiant power at the detector. So like one of the problems with the dispersion instrument is like we have the monochromator, which needs to be calibrated. We have need to make sure that all of the mirrors are in the correct place. We need to make sure that everything is moving as it's supposed to be moving, and it's not moving incorrectly. So we're not measuring a wavelength that we think we're measuring, but actually it's a different one, things like that. We have extremely high resolving power, which means that we have high accuracy, and we measure the whole range simultaneously, which means we can easily average over multiple measurements to reduce noise. So any inherent noise in the spectrum can easily be removed by just scanning several hundred times, assuming our sample doesn't change over that period of time, which in general it doesn't, but some do. Some will absorb water and things like that over time, which you can actually measure using FTIR. You can measure the absorbance of water as a function of time if you plan your experiment correctly. So parts of an FTIR spectrometer. So interferograms are collected using an interferometer. So the classic one is the Michelson interferometer. It's the one which is used inside of the FTIR spectrometer. So we can see here the workings of one inside of an FTIR spectrometer. So we have a moving mirror, we have a stationary mirror, we have the mirror which is allowing part of the beam to go out and part of the beam to be reflected here. And I can't wait. So it comes in, reflected here. This must be the moving mirror, and then this is the stationary mirror. So it goes through the stationary mirror, it comes back and is recombined here, and then this one passes through there, comes back and is recombined here, and then we can have our sample here. So an interferometer is an instrument that uses the technique of superimposing, interfering two or more waves to detect differences between them. So how does this interferometer work? So the light comes from a helium neon laser typically. So the light sources here that we're using for an FTIR spectrometer are different from what we were using before. We're not using a tungsten lamp anymore. We're not using glow bars, etc. Those are for dispersion and scanning instruments. These are for the FTIR spectrometers. So the light comes from the helium neon laser. So this is our coherent light source. So usually when you see coherent light source, it means that we're using a laser or something. The reason why lasers are coherent, we discussed before, but basically they have a lot of inbuilt ability to kind of protect against oscillations in the energy output. So half of the light is reflected, so at 90 degrees, to a fixed mirror, while the other half passes through to a moving mirror. So the coherent light source from our helium neon laser passes through here, and it comes onto a beam splitter fixed mirror. So this mirror allows half of the light to pass through to our to our moving mirror, where there is a delayed split beam. The other half is reflected to a stationary mirror positioned here. So you can see all of these things are at 90 degrees to each other. So this split beam is incident on the stationary mirror, where it is totally reflected back towards the beam splitter. Now it passes through the beam splitter and is recombined with any of the delayed split beam, but of course there will be differences in the recombined beam. So the beams are recombined, but due to different path lengths, they have an interference pattern. So remember our constructive and destructive interference that we learned about back when we were considering wave-like behavior. So the recombined beam passes through the sample. Our sample is contained here. Oftentimes in FTIR, we sandwich our sample between two disks. Usually it's like for example, a sodium chloride window or some other salt window, which will not absorb in the infrared region. Then once this recombined beam passes through the sample, some of it will, the differences in the interactions between the two beams will be measured, and then that will be detected. So the detector collects interfering signals and returns the plot of response versus mirror displacement, which is our interferogram. So for example, if the moving mirror moves a quarter of a wavelength, so about a half a wavelength round trip, waves are out of phase at the beam splitting mirror, and so we get no signal. Now, if the moving mirror moves a half of a wavelength, so we have 1 wavelength round trip, the waves are in phase at the beam splitting mirror, and thus we get a signal. So this is sort of the concept of what is happening with our interferometer. So the difference in the path length gives us a fixed mirror versus a moving mirror, and this is called retardation. So this is just slowing down, or like the difference in speed of the two waves. So this is the frequency domain. So the spectral radiance distribution of incident radiation. So here we can see the radiance power and the different frequencies, and then we can see that if this is the incident, then we can see that it once it is passed through the mirrors, one is going to be retarded versus the other, and so we'll end up with 2 peaks. And then what actually happens and what is actually read is something like this after it is passed through the sample. So we have here the initial beam, which has not been split. So the detector signal dependent on the optical path difference X within the interferogram. So here it is incident. This is the one that goes to the beam splitter. So you can see it is coherent and there are no differences. But after it is passed through the beam splitter and half of it has been modulated by the moving mirror, we can see then that it creates this beat pattern. Of course, depending on how we shift the mirror, we can change the number of wavelengths or fractions of a wavelength, which the split beam is different by. And then after that, we can get this interferogram after we have, this is the one that we will detect after the sample. And this looks much like the one that we saw earlier, where we were able to discuss how the spectral information was located here and here at the edges of our interferogram. So let's see a real example then. So this plot can be transformed to reveal the usual infrared spectrum that we are all familiar with via Fourier transform. So this is the interferogram after it is passed through our sample. So this is what the instrument is measuring at the at the detector, sorry. And then by doing this, doing an FFT, a fast Fourier transform, we can get this spectrum out here, which contains our spectral peaks, which are what we are going to kind of assign the different bonds to try and identify our how do we say this? Our molecular species that we are interested in. And that's pretty much the inner workings of an FTIR spectrometer. So there's quite a lot to deal with there. I think the major takeaways here are that what a Michelson interferometer does and how it creates 2 different path lengths for the light, and then what we're doing is we're measuring the differences between those so that we're getting our interferogram, which is basically just the spectrum created from the differences between what the 2 path lengths obtain in information from the sample. And then from that, we can Fourier transform that to get our actual spectrum. So our actual spectrum is not measured by the FTIR. It is what we're actually measuring is this interferogram. And then this interferogram is Fourier transformed to give us our spectrum, which we can actually interpret. There are some people who can interpret this and can understand this reasonably well, at least some characteristic peaks. But for the vast majority of us, myself included, this is what we need in order to be able to understand what our spectrum is telling us. So thank you for this session. Move on to the next session.